Bé, bona tarda, benvinguts, benvingudes, bienvenidos, bienvenidas a l'Escola de Camins. Welcome to everybody to this Civil Engineering School. So for me it's a pleasure just to welcome all of you to the school participating in one of the events we are organizing on the 50th anniversary of the school. So probably most of you know, but for the ones that didn't know what's happening, we are celebrating our 50th anniversary, and we have been organizing different things, a lot of things, but one of the ideas of former directors that we have been talking about was to organize this kind of seminars on the very important or the main topics that are challenging now in the civil engineering. So we decided to invite top high speakers as the one we have today here with us. And the series of seminars is entitled The Engineering Challenges That May Change the World. We have been talking about artificial intelligence. This week we talk also about oceanography. Oh, it's very difficult in English for me. Today we are going to talk about transportation, and we have planned others on urban planning, on bridge engineering, and other things. So you can find all the conferences in the web. There are ones has been done yet, and everything is recorded. Remember, for the questions, make serious questions that will be recorded and uploaded on the website. But I think it's very interesting because most of the topics that we have been talking about and we are going to talk about in this series of seminars are really important these days. So we have problems with the oceans. Last week we are now facing with artificial intelligence and digital twins and all these things, transportation, and it's a very important topic also in this new area for cities and for mobility, also urban planning. So I think this was a very nice idea. It was not from me, but I accept it. And okay, nothing else. Just to encourage you to watch all these seminars. And I want to thank the organizer of all of them, because these seminars has been organized by the professors in charge of the topic. So in this case, Professor Francesc Robusté and all the team has been hardly working on this event. So just to give you the micro to introduce the speaker and to talk about the transportation and the evolution of transportation.
Okay, thank you very much. And thank you very much to the director of the Civil Engineering School, Esther Real. Actually, she was part of my team when I was the director. She's much younger than me. And of course, thank you to Professor Jaume Barceló. The former director in charge of organizing these international seminars is Jesus Carrera, Suso Carrera. And then when he told me, okay, you should organize one about transportation, and then think about an international speaker. I said, well, Jaume Barceló. And then he said, no, international. Okay, James Barceló. Oh, yeah, then it's okay. It's okay. Yeah. Jaume Barceló, I'll introduce him briefly in some minutes, but he has been a well-known professor of UPC since the very origins, even before UPC was UPC, with the official name of UPC. Actually, he was hired not by UPC, but by the Industrial Engineering School, the school. First, the school where before, in this case, the Industrial Engineering School in Catalonia, the oldest engineering is the industrial engineering. In Madrid is the civil engineering. So he was hired by the Industrial Engineering School before the Technical University of Barcelona at that time, not Catalonia, of Barcelona at that time, was created. And he has been developing many things, but especially one well-known microsimulator, which the name is AIMSUN. Of course, him and his team. Some of them are here. And AIMSUN is the fastest and the microsimulator with more users in the world. So probably some merits. No? You should get some medals at some point. No? Okay, but before that, I'm going to take a small parenthesis of some minutes to talk about a little bit reflection about what we had at the beginning about transportation, and not just transportation, what we do, Barcelona Innovative Transportation Research Group, but the infrastructure that was first. No? The first is the infrastructure. In our profession, the main point is the infrastructures of two things, basically, water and transportation. Everything else, structures, geotechnical engineering, whatever, yeah, of course, because we need that because we want to build infrastructures for water and for transportation, mainly. Of course, here I put what we have for pillars, 4 columns, what we have in our civil engineering school of Barcelona. Railways, roads, then transport, and then mobility, and I'll tell you a little bit the difference. It's something that we discovered ourselves. I remember talking to Jaume 20 years ago, and they said, no, mobility has nothing to do with transportation. And I said, well, okay, then we take your words, and then we devised a process to formalize a master's. Well, and here, probably, if you are students of mine, some of you, probably you have seen this also, this picture. The different technologies applied to transportation. The first one, and the most important, is civil. Why? Because the infrastructure is the most important. And then, of course, you may have a very nice vehicle without wheels and without something flat. It's difficult, no? Unless you fly. And then industrial engineering. It's in the last 150 years. And then lately means several decades. All the information technologies. Of course, all the information technologies they improve, but not substitute the previous technology. I don't know what happened. Okay. And as you can see here with this lemma of the civil engineering school, they always use the, moving. It's always transportation related. Okay, let's talk a little bit about railways. Railways. Well, basically the team, it's reduced. It's because they only had one subject at the beginning, one subject. I remember coming on Saturday morning, this professor, Andrés López Pita, it's the only professor and one of the earliest professors we had in our school. Is professor since 1983. He's retired. He retired some years ago. And I remember coming to the school on Saturday mornings, and the time was variable because he was coming from Madrid, and at that time, the air shuttle, Madrid-Barcelona, they were not very punctual. It could be, now imagine that the class was at 12. Well, today was at 12. Tomorrow is at 12:45. Depends on when he was arriving. But at that time, now people would be, the students would leave. No? But at that time, we were thinking, oh, this guy is coming from Madrid just to give us one class of 1 hour and 1 hour and a half. It's a big sacrifice. It's a big personal sacrifice. It's not 15 minutes. No. He's spending a whole day just to teach us. So we were paying a lot of attention. I remember when SNCF, they introduced this high-speed rail Paris-Lyon in 1981. In several months, he managed to have this movie, this kind of, this is how we were watching movies in the movie theaters some years ago, some decades ago. And he managed to get this movie, and then we saw this train for the first time running at these very high speeds. He was chancellor of the Catalan Railways president, Albert Vilalta. Then Albert Vilalta became deputy minister in Madrid, and also López Pita had some influence in this sentence to define the high-speed rail in Spain. No capital of province in Spain at more than 3 hours in high-speed rail from Madrid. Very prolific professor, many books. Here you have a sample, probably I forgot some. A very good expert about the rail, the infrastructure. He got several awards, and he belongs still to the Royal Academy of Engineering in Spain. This was a little bit the team, and I have to tell you that having this research center, CENIT, was the seed to collaborate between us and to create a team. Otherwise, small research groups are, formed by 1 or 2 people, and this doesn't create a team. From one subject in 1980, railways, that we used to call it trains, was shorter. Now they have several subjects shared with roads, construction of transportation infrastructures, shared with roads, and then high-speed rail lines management in the Masters of Civil Engineering, and pretty soon another subject in the Master of Urban Mobility, Railway Transportation. The team, they had several part-time professors, assistant professors, Ángel Herrero, Sergio Morán, and Adriana Bachiller, and Carlos Casas, they're still. And now that the professor is retired, most of the teaching relays on Benedicto Lizcano, Dr. Benedicto Lizcano, and we just hired, with the help of Ferrocarrils de la Generalitat de Catalunya, that gave money to the UPC, with the collaboration of the school, we just hired a lector, Zacarías Grande, which is going to be the future. Okay, roads. This was prepared by the roads team that now they are watching an exam, everybody, so that they cannot be here. Okay, this was the early days, the early years. Some people passed out already. Joan Comte Guinovart passed out, the first an expert about roads, and then this guy brought 2 people as young people, as a young engineers, José Vicente Solano and José María Alonso Viarge. I remember one of these subjects by José María Alonso Viarge. I didn't take it, but this kind of legend that the students talked. That this guy was talking about. This is before computers. We are in the 70s, and then this guy was talking about roads, the layout of roads as a swath, using these differential varieties. Frenetary Hedron and these kind of things, everything mathematical. Then we had this Juan Antonio Fernández del Campo, also passed out, but we used to, he was coming from Madrid, we used to call him the minister, because a guy, he was, talking, really, like a minister, with a very nice suit. I remember the first class, well, the cities are not meant for cars, but with something obvious, but he was making it really. And then Pablo Novell also passed out. He was teaching road layout. And then the first professor, full-time professor they had was Felix Perez, who just retired some years ago. But is the first full-time professor coming from Santander. And then they had several assistant professors, Jorge Soler Peix, Joan Almirall, Francisco Criado, Eduardo Fernández de Villalta, Xavier Massaller, Enric Font, Ramon Botella, and Josep Pedret. Who are the team right now, the full-time professors? Rodrigo Miró, Adriana Martinez. Rodrigo is full professor, Adriana Martinez associate professor, and the youngest, Teresa López, lecturer. They have the research group is MATCAR, Materials of Roads, Material de Carreteras. Well, they have a lab, a laboratory. The first equipment is a picture of the first equipment they bought, they acquired, Los Angeles Drum. I forgot what this was, but probably. And then now they have 2 dynamic servo-hydraulic presses. They have worked with many standards about, they are very good experts about pavements. They have 7 copyrights, 45 research and development projects, 74 scientific papers, 24 PhD theses, and 450 degree and final degree and master's thesis. And these are the subjects. They had several names, and the ones in bold are the ones, the current ones. Transportation infrastructures, construction of transport infrastructures, conservation, airport management and maintenance, and then road networks planning and management. Some of them are shared with the railway engineering guys. And last is our team, my Barcelona Innovative Transportation Group. I'm going to talk about transportation and mobility, and pretty soon you will see that Jaume Barceló played a key role in this. Well, the early days, late 70s. I skipped this because I didn't have this. The professor Juan Domingo Cox, he died. But then the first professor I had was Mateu Turró. Was the first professor with an international background. He got a master's in Michigan and at Ann Arbor. And then he finished a PhD thesis here in Barcelona. But then pretty soon he went to the European Investment Bank. And then he called me and said, well, you need to finish the PhD thesis. So that was in 1988. When are you finishing? That was in May. I said, at the end of the year. No, you need to finish before, because you need to be here at the beginning of September to teach the classes, because I'm going to the European Investment Bank. So you can imagine. And then with me, I had this, the opportunity to get some master's degrees and PhD at UC Berkeley. So we had some international standards about research, also the first publications in scientific journals in transportation. And then in some years later, I was teaching not 20%, but 100% more than what I should teach, because I never had somebody helping. And then at the end, I said, well, I'm not going to teach the key subjects until we solve this. Of course, I talked to my director of the school, Antonio Aguado, first, so I'm going to do this. And then, this was solved in 1 month. It went to the cloister of UPC, the rector called solve it. It was in 1 month. I had the promise that pretty soon we are going to hire somebody, and then here comes Magín Campos, who came from over there, who came from Santander. Thank you, Magín, for this big, leap. Magín got his PhD thesis in 2011. Then some collaborators that some of them died already recently. Jacint Soler, expert about buses, and Ole Thorson, very well known because he came from Denmark and he stayed in Barcelona. And he was this kind of humanist guy that, dealing with pedestrians and road safety, these things that was a good complement to what we teach. Fede Sabrià, a friend from UC Berkeley, he's a professor at IES Business Administration School. So here we had the list of part-time professors: Jacint Soler, Jesús Urarte, Fede Sabrià, Ole Thorson, José Enrique Pérez, a consultant, Manel Villalante, Aura Plomet, the city of Barcelona, Josep Aimamí, AIMSUN, Paolo Rinelli too, Marcel Sala, and Darian Heming. This is I put this medal because this is my contribution after almost 40 years, is transportation being treated in singular in Spanish. In Spanish, I don't know why they call it in plural, transportations. In the rest of the languages is in singular. So this is my contribution. It's pretty simple, but has a lot of deep meaning. Instead of talking about modes, we talk about concepts: operations, pricing, demand, appraisal, network layout. The same concepts apply to many things. The transportation and mobility from a system and service and user perspective. Well, we have done many course notes, institutional books, 220 transportation seminars, 48 research seminars, something apart, no? 18 courses by international professors, 40 PhD theses, 500 master's and bachelor's theses, and 200 papers in international journals. As I told you, having this research center, CENIT, the first director was Andrés López Pito, the second director myself, was a possibility to become a team. This is with Carlos Daganzo. We signed an agreement with the rector. We had Soler Peix. These are courses and that we organized. Another positive thing that was a bit of luck is that we had these toll motorways, ACESA, and then they evolved into an international group. Actually, the name is Abertis, and they are still the largest group of private toll motorways in the world. The headquarters, they are still physically here in Barcelona, even though now the owners are Italians and from Madrid. We had this endowed chair, and then we could give prizes, organize. Well, you have money, you can do many more things. We could pay for some financing master's thesis, PhD thesis, whatever, seminars, courses, etc. Two key steps for me also, that was, they were a sacrifice at the beginning. Teaching in the Nautical Faculty of Barcelona. So I was overloaded, and then a professor called me, Germán de Melo, I would like you to teach here some logistics for our undergrads. And I said, okay. And then finally we have several subjects here, and Magin and Manel Grifoll right here. Manel Grifoll actually is the missing link in port engineering and transportation, because usually port engineering in this school is related to the water, no? To the sea and the ocean side and the coast, the movement of the water, no? And then we need a link between, because one thing is the infrastructure, but then what for? Or once we have the port, and then the port is moving freight and containers, okay? And then another thing was teaching also in the industrial engineering school. They had this rector that was an industrial engineer, and he was really interested in logistics. It looks like he had a family business, moving parcels in Al Prat, and then he was really interested in getting this degree in logistics. And I said, okay, we can say I don't participate. No, we'll participate. We'll go to teach in industrial engineering. And then this pretty soon became a master's in supply chain, transportation, and mobility. Of course, it was a luck that I was the director of the civil engineering school at that time. Otherwise, the things probably, they wouldn't have been the same. But here I put this triangle because, they were insisting, no, this master has 3 legs. One is supply chain management, industrial engineering. Another leg is transportation, and they knew that transportation was for civil engineers. And the third leg was, something, mobility. Has nothing to do with transportation. We remember with Jaume saying, well, transportation and mobility, mobility is broader, no? It has a social aspect, demand aspect, no? Not just supply or engineering side, no? And I said, you know what? We were fighting a little bit to get the power of this, no? To the balance, the Roman balance, to balance it towards the civil engineering or industrial engineering. And then I thought about this strategy. I talked to Jaume, said, well, nobody will consider a boss of this that is either a civil engineer or an industrial engineer. But what about a physicist? And a nice guy, like you. And are you willing to accept this? So I proposed, okay, the supply chain, they had a professor that was at that time was the vice rector, but he didn't want to be the boss here. They delegate this into an industrial engineer. Transportation, Lopez Pita is the guy with more research stretches at that time. Mobility, I just became professor. I just became professor 1 or 2 years before, and I said, myself, since there is nobody else, mobility. And then the director of this, the coordinator of this, Jaume Barceló. And then they had to approve this because we were all professors. There was no alternatives, and so they had to. We managed to invest Carlos Daganzo, my director of PhD thesis, doctor honoris causa in 2012. Now, this master's in supply chain transportation and mobility was turned into masters in urban mobility. Of course, we don't have so many students that to have extra. So this was passed from the master in supply chain transportation and mobility. We got rid of some very specific industrial engineering subjects, and then this became the masters in urban mobility. And of course, we need to control these things, so it's always really nice to have people of our BIT research group. Miquel Estrada first as a subdirector of the Masters of Civil Engineering, and now the coordinator of the European Institute of Technology, and then Francesc Origuera, subdirector of the Civil Engineering School and coordinator of the Master in Urban Mobility. Well, we have many subjects, from one in the 70s, economics and coordination of transportation. All the subjects in Spain that were not related to infrastructures had this name. And the people were related to railways. In Madrid and Valencia, and everybody was related to railways. And then in the new plan of 1978, we had 2 subjects, but only 4 people of this specialty of transportation planning and transportation economics, and now we have a bunch of subjects. This is our team today. We are these 7 full-time doctors, 2 professors, myself and Miquel Estrada, who is in a trip right now, but he became a full professor. Francesc Origuera and Manel Grifoll, pretty soon. They are associate professors, but pretty soon they'll become full professors. And then José Magín Campos, Hugo Badia, and Margarita Martinez. And then we have a bunch of collaborators, part-time, some of them with a PhD thesis, some of them have been PhD students of some of us, like Enrique Jiménez, Marcos Medina, and some of them are doing the PhD thesis right now, like Clement Lemardelais. Projects, lunches, we have a lot of fun. And this is it. I think, I don't know, but I think as a group of all the transportation engineering, railways, maybe railways need a little bit of this kind of renewal, no, of people. We have the people, but they just started. Roads and transportation, I think we are on the right track. So thank you very much. And now it's time to present Jaume Barceló. He's, as I told you, he's a physicist. He's got a PhD in physical science. And he became professor of the Department of Statistics and Operations Research here at the Technical University of Catalonia. He is Professor Emeritus since 2014. He has been, well, several things. He has been the scientific director of the transport and ICT projects and at the InLab of the computer science faculty. He has been teaching in the computer science faculty and also in the mathematics and statistics faculty. He became also the director of CARNET during a couple of years, 2015, 2016. And I remember he invited me to teach a lecture, and then I said, well, but I'm going to be a little bit, I don't think they're going to like it. And then he said, well, no, it's okay, it's okay. And after the lecture, they never invited me again. He's author of more 140 papers, but he got several awards, no? Like medals, Narcís Monturiol Medal of the Regional Government of Catalonia, the Traffic Simulation Lifetime Achievement of the Transportation Research Board. But probably his main contribution, he spent some years, 3 years, as a strategic advisor of the PTV group on transport models, but probably his best achievement with his team was to develop this reference micro-simulator AIMSUN. With his team, that at that time he was calling this team the Laboratory of Operations Research, Investigació Operativa, and Simulation, with the acronym LIOS. LIOS means this is messy, it's messy. So without any more introduction, Jaume, we are here to listen. Whatever your reflections will be welcome, and probably will take note of this. If you don't mind, we're going to go downstairs so that we can pay attention to you better.
Just a second. Okay, thank you very much for the nice presentation or introduction. I'm very grateful to the School of Camins because this invitation to give this talk represents for me a recognition of the work that I have done. I am also very grateful to BIT and the Français Robuste because I know they have been the engines behind this proposal. And obviously, I thank all of you very much for your being here, because maybe you think that I have something interesting to say, and I expect not to deceive you. Well, the title was suggested by Francesc, that of making a brief history of modeling, and then say a few words about my thoughts on what's the road ahead, what's to the future of modeling. Well, you will allow me that first I will restrict this brief history to even
Press again, yeah.
Okay. Even more brief, in the sense that modeling is a very wide world. So I will talk only about some, not all, some of the models to which I have contributed. And then you will allow me to give a kind of a personal touch to this presentation. And then this talk will be a kind of a journey through this modeling jungle. And this represents a story in which you have to overcome certain risks and difficulties, like when you climb a mountain. But currently, there is a trend to present these achievements only in personal terms. I am who had conquered the mountain. But explore an unknown territory, like was the modeling territory 50 years ago, we have to bear in mind the time perspective, was just exploring something unknown. And this is not a work that is done by a person, but is done by a team. And it's only the joint effort of the team what allows you to reach the summit. Yes, I'm going to talk about modeling, but let me, before entering into the modeling details, make some reflections about what are the models and which is the purpose of the model and the models and the use of the models. So first of all, I would like to highlight that a model is not the reality. The reality for me will be, in general, a system, and obviously in this context, a transportation or a traffic system. A model is only a formal representation, and I will highlight this term formal, because that represents that we use some very well-established rules and terms in terms of a formal description of something. And it's a formal representation of this reality. And what I will like still highlight even more is that it is only a tool. A model is only a tool, but it's a tool that belongs to the core of what we know as the scientific method. So in that case, for me, transport modeling means apply this methodology to the systems, the transport systems. And then I like very much this picture from René Magritte, that this surrealist painter that recalls us that one thing is the representation of an object and another thing is the object. Please don't forget this. Then model can be defined as a formally organizing what we know or we think we know. I think that this is very important. We think we know, because maybe we not always have the perfect knowledge of the system. About a system, and which is the purpose, predict how the system might behave in the present, future, or past. Are we able of reconstructing the past, as well as how it might respond to external influence? In the case of transportation systems or traffic and transportation system, what means external influence? That means a policy, an intervention, trying to with the objective of trying that the system behaves in a certain way. Well, it has a very well-established methodology. I will not go through the details because otherwise, as some of my students have been recalling me today, I could be able of spending more than 1 hour talking only with this slide. But anyway, what I would like to highlight very briefly is that it starts with acquiring knowledge of the system. And what is acquiring knowledge of the system? Is observing the system, measuring the system, processing this data, and extracting some information about this data. The base hypothesis is that the data contain information about the phenomenon that has generated them. So we try to get insight on which is this phenomenon through this data processing analysis. And this is the process that of knowledge acquisition. This knowledge acquisition allows us to formulate modeling hypotheses. That means how do we assume that the system is working, is evolving, and then The 1 million question is whether we are able or not of translating this modeling hypothesis into the formal terms that we call the model. But talking about models, this is a kind of recommendations after more than 40 years of working in modeling. For those who working with models, is please don't look for the holy grail of models. What that means, look for the unique model that solves all your problems. For me, Marvin Minsky, one of the fathers of artificial intelligence, around 60, no, almost 70 years ago, formulated the problem in a very clear terms. It's what is called, what is known as the Minsky's triad. An object, M, is a model of a system, S, if it can provide valid answers to the question of observers of the system. Consequence, there is not such a thing as the unique model, are the different models depending on the objectives of the observer, which are the questions that the observer tries to answer with the use of the model. But that means that if we are not looking for the Holy Grail, then we must be clear about which are the questions we try to answer. Then we have to select the type of models. And then we have to make sure that this model is able of providing valid answers to the questions that we try to answer through the model. How this stability is established, I will say later on a few words about this. It's a combination of methods, criteria, and data. Well, I think that traffic and transportation systems are a perfect example. We have a unique system, the traffic and transportation system. But we may have different objectives with our system analysis, from transport planning to traffic operations to something between. Then that means that the decisions that we are going to take on the system through the use of the model, that means the answers to the questions that we are looking for using the model will be completely different in every case. And on the other hand, the data that we need, and very important, the data available, because quite frequently, the limitations of modeling activities is just the availability of the data. We need the data that are not available. And is for me this example of one system, multiple models. That is the perfect example of Minsky's trial. But just to conclude this short introduction to modeling theory, as I have mentioned from the definition of the model, our main objective is use the model to support decisions. Decisions can be made in many different ways. In 99.99% of the cases, it's just by intuitions. I believe that, I think that, I know that. And in the other cases, the rational decision is trying to be assisted by a decision support system. And what's at the core of a decision support system is a model of the system, this formal representation of the system. But a caveat for the enemies of the models that are a multitude, they are very happy quoting George Box, that is one of the fathers of modern statistics, and because of that, one of the fathers of most of the models that we are currently using, when he said, all models are wrong. Okay, this was in a paper. Well, incidentally, at the bottom of most of my slides are the references to the papers or the sources I have used to prepare that. Then he stated this in a paper. But what in a very biased way, many people forget is to complete the quotation. And the quotations says, but some are useful, which is also stated in that case in a book that was written along with Draper. Then The 1 million question is what makes a model useful? And is the validation and calibration what provides a quantitative answer to this question that finally what mean is whether the model predictions faithfully represent or the reality. How far is the reality from what I can observe in the reality from what the model does? And again, this has behind a very well-defined methodology in which we have the set of the operations that we do with the real system. That means the observation, the measurements, and so and so. And then what we do with the model of the system. And finally, this is the core of the process, the comparison between what we observe and what we predict with the model. Only when this comparison is acceptable according to certain criteria, then we can rely on the use of the model. Otherwise, the model could be a very nice exercise, but of no use. Okay, let's move into the objective of the talk. What was in the beginning? In the beginning was the microscopic models. How I became a transport modeler. It was very simple. In 1981, the Dirección General de Tráfico of the Spanish government contracted a consortium to develop a traffic management project on the National 3 in the section between the Barajas airport and the city. And then it was Gardeta, do you remember him, was in the panel who defined the project. And he was back from Berkeley a short time before that. And they said, okay, we need a model. So the word model, simulation model, was written in the pliego de condiciones, the conditions of the project. And the project was awarded to a consortium of basically two companies. One company that was ISEL, and another company that was the company of the Ministry of Industry. Later on, these two companies merged into a unique company, ISEL, and that was the origins of Indra. So there is a long story about this. Then I had been doing some works, simulation works for ISEL. And then ISEL, they contracted me to do this simulation work. Because I was expert in simulation, although I had never done any traffic simulation. So I had to learn. I started to learn, and then I discovered that the first order models. And I thought, oh my God, coming from physics, this is very simple, this is very easy. These are just the hydrodynamic continuous equations of the physics that I had studied when I was studying physics. So that was very happy. Well, this is very easy, no problem at all. Then I learned about how to solve the partial differential equations through the corresponding partitioning in discrete space and time intervals, the current mesh of the numerical methods for the partial differential equations. I discovered at that time, I say I discovered because I was learning the fundamental diagram and how to use the fundamental diagram to solve this. Then I was curious, then I found that it was something else. It were the second order models. Then I fall in love, I have to say intellectual love, with the Pines model, including these inertia and viscosity terms that were trying to anticipate the driver's reactions and things like that. And with all this, I coded myself in Fortran 4 at that time, a small program just to implement a pilot project with the objective to prove to the Dirección General de Tráfico that, okay, modeling is a valid methodology and we are in conditions of building the right models to do that. Then I was asked to make the presentation at the Dirección General de Tráfico. And to my surprise, it happens that the Dirección General de Tráfico considered that my presentation had covered the objectives of the project. End of story. I never developed the full Pines model that was my original intention. I include here, just for documentation, this will be a summary of the developments on these macroscopic models based on traffic flow theory at that time. And I started a very nice collaboration with Panos Mikolopoulos, that at that time was one of the gurus of the macroscopic models, and also with Marcos Papageorgiou, that I assume that some of you know. And obviously, later on, because I'm talking of the early 80s, it was 10 years later when Carlos Daganzo appeared with the cell transmission model that was an alternative approach to this type of modeling. And then, well, some of you remember the big storm when Carlos Daganzo declared the requiem for the second-order models. But then it was a very strong response to that. And today, I think that this is solved in some sense. I will drive your attention to this Chronos and MetaNet because we continue a relationship with them. And what I would like to highlight is another aspect. Well, so far I have been focusing my attention in the mathematical aspects of the modeling. But you have to implement the models. And you are implementing the models of a physical reality. And the physical reality, a motorway in this case, has a geometry. So that means that the model has, simplifying the situation, at least two main components. The physical model, the geometry of the model, and the mathematical model. And you have to put them together. Then in the mid-80s appear the first graphic systems. And then it was the possibility of thinking of developing tools to build the network, the road geometry. Well, this is what Chronos 6 in the 90s, at the beginning of the 90s, did. They were trying to analyze which were the main geometric components of a motorway. And then they define a graphic module for each one of them. So in that case, you had a screen with this is in justice the capture of one screen, and then you were selecting on the screen the different models and then merging or joining the models, and you had the model of the geometry. Then you had some dialogues to define the parameters of each one of the modules in terms of the flows, the turning proportions, and things like that. And then what you have to do is just to link this with the corresponding numerical equations that I show in the previous one. Furthermore, you could, at that time, you had not an automatic graphic output, but you could produce an output that you can digitize and process after that. And then you can get, for instance, very nice graphics that help you to understand how the model was working and the reality was working. For instance, this is the typical study for a motorway comparing the flows in the motorway for a given demand in a given time period without RAM metering and with RAM metering, just to show how the control system could assist in alleviating the problem. Okay. After some time, I recall you that my deception was that the Dirección General de Tráfico considered that my presentation was the project, not the development of the model. And then, in that case, the municipality of Barcelona, I have to thank the municipality of Barcelona at that time because it was very contributive. In fact, Pasqual Maragall, when still he had memory, each time we met, he always remembered me. The municipality of Barcelona funded the development of AIMSUN. We put the seed capital to develop AIMSUN. And this is true. It was with this project, that is a project that was co-funded by the municipality and this commission assessora. Incidentally, this was a short period of time in which it was a real money for research in Spain. After that, no more repetition. But anyway, then we had to develop a project for the municipality. And then this is the way in which I set up the research group LIOS that Robuste mentioned before in the presentation. And this was this Laboratorio de Investigación Operativa y Simulación in our department. Okay, but then immediately I realized that we were working in a completely different scenario. In a motorway, in a freeway, the only flow interruptions that you have is due to congestion, the stop and go. But in a city, something different. In a city, you have crossings and you have traffic lights. And then you have interrupted flows. How can you properly deal with the interrupted flows? A motorway is a linear structure. And the vehicles enter the motorway through the entry ramps and leave the motorway by the exit ramps. But they don't follow paths, specific paths. But in a city, in the network, road network of a city, you have origins, you have destinations, you have paths from origins to destinations. From one origin to one destination, you may have multiple paths. So how to deal with this? So that means that we had to change the simulation approach. And in that case, the simulation approach that I found that could be the right one for that will be what we call the microscopic simulation. What means that? Finally, what we are doing is just to try to find a way to have a tool to analyze traffic flows. Flows. Remember the hydrodynamic simile. Then you can deal with the dynamics of a flow from two approaches. An aggregated approach and a fully disaggregated approach in which you try to describe the dynamics of the flow, describing the dynamics of the individual components of the flow, the particles. And the particles in that case are the vehicles. And then in that case, you get the possibility of interrupting the flows and making that your particles follow paths across the network. So that was the idea. And then I had to learn again something new. Then first, which was the state of the art at that time? At that time, we are talking of 1985. The only existing tool, well, maybe in some universities, some research groups, they have developed something. But the only I found at that time was NetSim that had been developed by the Federal Highway Administration. The problem, well, the NetSim was very primitive, and the main problem was that the building of the geometry of the network was extremely painful. You have to digitize the geometry and then input manually digitization into your. It was a nightmare. It was not until 1998 when the combination of NetSim and FreSim, that was a follow-up of Pioneer's model for motorways, became the CoreSim, again sponsored by the Federal Highway Administration, in which they included for the first time graphics. But 1998 was 13 years later, after we started our project. So we could not count of this. Just an advertising. from the very beginning, I realized that we need to set up international connections because we had no reference in Spain. And this is why I set up my relationship with Marcos, with Panos, with Xin Miao Xin, that at that time was in Oak Ridge, this laboratory in which that was developing NetSim, with David Bretherton, that was the developer of Scoot, that was at that time the most advanced traffic control system and things like that. Again, the Municipality of Barcelona financed the symposium, and then I was able of inviting all these people, but at the same time allowed me to set up a very strong networking of it. It was quite useful, if not for the city, at least for the LEOS research group. Okay. What, in a very, very quick way, what we did in the following years. First, try to find efficient solutions for the building of the model building of the geometry of the system. So we realized that we had to work with GIS, with Geographic Information System. We developed the tools to import the road network from this. Then, because if we were going to move into the detailed geometry required by the microscopic modeling, so then we had to be able of reproducing the geometry in all its complexity. As I mentioned before, we had to be able of identifying origins, to identify the destinations, to identify the routes, and identify the ways of choosing the paths among the set of routes between origin and destinations. And obviously, we had to be able of developing the tools to include traffic control. Traffic control, in that case, it was an input to the model. Incidentally, in the early years, when we go to the municipality to ask for a traffic control plan, they provide us with a bunch of papers, of the photocopies of the documents, and then we had to enter manually. Fortunately, things have changed substantially. Now, most of them, they have, for instance, the signal settings in terms of Excel files, and then you can import the geometry, the allowed turnings, and the facings in an automatic way. Okay. But a microscopic model is not only the geometry. You need some, let's say, core models that are at the engine of the simulation. Obviously, it will take me more than the time that I am allowed to go through the models. Then let me just say a few words about car following. That is practically the most important of the models. The one describing how the vehicles move, the dynamics of the vehicles. Okay, a short description of the bibliography. I discovered that the people interested in car following had studied the problem since, at least from a mathematical point of view, since long before we started our work. Then this slide can be considered the car following theory in a nutshell. The empirical facts that were found by empirically by what was known as the General Motors team, headed by Robert Herman, Dinos Gassis, Potts, Chandler, and then they did some experiments. On these experiments, they found an empirical fact that there is a high correlation between the response of a driver and the relative speed of his car and the one ahead. That's the follower and the leader. That the modeling assumption will be that each driver will react in some specific way to a stimulus. The question is, which is this stimulus? And then the discussion was that the stimulus, taking into account that the laws of motion could be described in terms of differential difference equations, systems of differential difference equations, then the stimulus could be, for instance, the relative speed, the relative headway. Well, you can define many concepts of a stimulus. Depending on which is the concept of a stimulus, you will get one kind of model or another. And then the sensitivity is why drivers doesn't perceive all of them the stimulus in the same way. I always, when I was teaching at the master, I always put the example that not every driver reacts like Fernando Alonso or Schumacher or at this time or Verstappen or any of them. So then that means, that is what makes for me one of the most critical aspects in transport traffic modeling. Is that if we were dealing only with a mechanical system, we will be very happy. We know very well how to solve these different systems of equations. But the problem is that the parameters in these systems try to try to emulate the human behavior in driving. And then you enter with a set of parameters that are not so easy to calibrate and to define, like the sensitivity to the stimulus, the reaction time, etc. So we have these vehicles, we have the speeds, the positions, we have the distances, the lengths of the vehicles, and then you have the different relationships with the definitions of which is the speed, which is the relative velocity between two vehicles, which is the spacing, which is the acceleration of the vehicle, and things like that. And from that, depending on how do you define the stimulus, you can get families of car following models. For instance, one of the most famous is that of the Hermann Gattis model of the General Motors, in which what they have is that the reaction of the follower vehicle after a time capital T that represents the reaction time of the follower will be accelerating or decelerating depending on what? Depending on the relative speed. And what he considers is that the stimulus is a function of a general parameters and two parameters A and B, and this represents the current speed and the space gap between the vehicles. Well, this is a solution to the problem. What I like very much is the general theory that was developed by a mathematician, Eddie Wilson, just 10 years ago, in which he puts all this into a general mathematical form and says that any car following model can be described in these terms of a functional, depending on which type of functional you get one model. But from a mathematical point of view, it's quite useful because it allows you to analyze the stability of the model and things like that. But there is another possibility. Another possibility is assuming that the people is not stupid. All models are based on hypotheses. Traffic models, as I mentioned a minute ago, is assuming some behavioral human hypothesis about human behavior. And then assuming that humans are not stupid is a very strong hypothesis yet to be proved. Anyway, if we continue with that, assuming as modeling hypothesis this, we can ask for the following question. Let's assume that this is the leader and this is the follower. Let's assume that the leader decides to stop, to brake to stop suddenly. This will be the distance, according to the laws of the mechanic, that it will take the leader to come to the full stop. The follower will realize after a certain delay that the leader has started to stop. So the follower will try not crash and then will try to brake as much as possible. And if it succeeds not crashing, that means that this will be the distance traveled traveled until get to a, let's say, safety distance from the road. Well, if we accept this and we take into account this is just a simple exercise in cinematics, then you get to this functional. That is a function, it is telling you the relative positions, the relative functions at every time, depending on the speeds and the braking capabilities. And it depends of a function that is the braking function. Is the function that determines, depending on the hypothesis you formulate about the deceleration, which will be this distance. Then you can assume that is a constant deceleration, a linear deceleration, an exponential, and you can get, in that way, a family of models. One of these models is the Gibbs model. And that was the model that I decided to choose for AIMSUN. Why? Because after performing, well, you can see that this is the typical analysis that is conducted with an Excel sheet. And then I found that the behavior in the relationships, velocities, distances, was behaving more or less as expected, was quite rational, that if we were considering a section and we were taking into account the variation of the acceleration, what is known as the acceleration noise, it was what theoretically you expected. In the same, if we were putting this in relationship with the reaction time, or if we were simulating a leader-follower, that will be the trajectories, and that will be the speed. So we found that the Gibbs was providing a very acceptable behavior, and that was the way in which we decided to implement Gibbs in the AIMSUN model. Let me go shortly back to the origins of that. And then maybe you have heard about the methodology macro, meso, micro. Macro, in that case, will not be the continuous models that I described before, but the long-term planning static assignment models. Meso, I will say a few words about the mesoscopic models later on, and micro is the microscopic models that I am describing. Then I can claim that the origins to that, and Esteve is here, and I think that is a witness of that, because he was suffering most of this project. That the following is AIMSUN. If AIMSUN started its development with this funding from the Ministry of Science and the Municipality of Barcelona, later on we became the simulation providers in the European Union. And that allowed us to participate in a very short time, in many projects. And this was what allowed us to develop AIMSUN. But I would like to refer to three basic projects. And I will mention only Asterix, that was a simulation tool for evaluating road transport informatics. Incidentally, it was Dirk van Vliet, the father of Saturn, who invented the acronym. Was a project in which we developed for the first time this idea of creating a general framework in which the three modeling approaches could dialogue and not become independent of each other as at that time. I give here three references that are published references, so they can be accessed, that I think that prove my assertion. Claire was the first time, and I'm talking about 1991, in which we tried to see what could be achieved combining artificial intelligence for traffic control and the microscopic simulation. And Socrates, that was coordinated, the principal investigator was Philips Research Laboratory. That was 1991. Mobile phones doesn't exist at that time. Exists only as a laboratory product. Then Philips in Eindhoven, at the Philips Research Laboratories, they had equipped the road around the factory with a mobile system for experimental purposes. Then that was in which we became in that way the providers of a simulation test bed to test navigation. But so it was 33 years ago. That's okay. Then more things. This is we go very quickly through this, but I would like to highlight something. When you come to develop the development of a software platform for modeling, you realize that it's far more than only the mathematical models. I have mentioned the developments for the modeling the geometries of the systems, because we are modeling a physical system. But how you put this together in an efficient way? If you want that the macro dialogues with the micro and with the, how you do that? And this is, and for me is the only message, this represents the development of an integrated environment, and this could be done only with a multidisciplinary team. Okay? This is the team who reached the top, as I mentioned, I show in my preliminary slide. And so that means that there was a lot of innovation in terms of the concepts of data structures. That is what makes, in some sense, AIMSUN to be so successful. And so, this is a list of the many different projects in which AIMSUN was developed. I will highlight very short comments only about 3 of them. The first is Petri. Petri was a project of the High Performance Computing Initiative of the European Union, whose coordinator was Matteo Valero. That at that time had the CEBBA, the Center, the European Center for Parallelism of Barcelona. That was the precursor of the BSC. And then he invited me to join him in a team, and what we did was to parallelize AIMSUN. When Frances made reference to the high computing performance of AIMSUN, these are the roots of that. And of a very successful collaboration with CEBBA this time. And, okay, sorry, I am. Then, GIDAS were a set of projects funded by the Dirección General de Tráfico before the Olympics, between 1999 and the Olympics. And then this allowed us, along with Professor José Cuena from the University of the Technical University of Madrid, that he was a civil engineer that later on moved to computer science, informatics, and became the leader of the applications of artificial intelligence to transportation. Then what we did in this case, I will describe very briefly, was to combine artificial intelligence with microscopic simulation for traffic management. And last but not least, enterprise, that was first was a European project, and was the European project that enabled us to develop the larger model we had developed so far. There was the model of the whole motorway network of Hessen in Germany. And later on, it became the basis for the development of was the AIMSUN Online, because they wanted the traffic management in real time. Let me very briefly mention 3 particular projects that play an important role further than the research and development projects. Maybe you will identify here the Ronda de Dalt and the Nus de Trinitat. That was a very strong controversy in Barcelona with respect that we were risking that the Ronda de Dalt was not completed for the Olympics because of the differences. And then the municipality was wanted, because they had funded AIMSUN, they wanted us to prove that their design was the right one. And then, unfortunately, what I was able of proving was something that Acevillo didn't like very much. I was proving that if we are continuing with this picture of the fluid, that the traffic for a certain demand, level of demand in the Ronda de Dalt was as a fluid in overfusion. It's like when you have, for instance, water still in liquid, as a liquid, but at minus 10. It can be, but it's a completely unstable system. And what happens at any small perturbation makes it frozen suddenly. So if we created any small perturbation in the traffic, the Ronda de Dalt became frozen, as it usually happens in practice. So at least that was an empirical proof. Anyway, I save you the Acevillo's reaction that was not exactly very polite. But anyway, the Mecca. This is the Arafat. This is what the pilgrims do in the third day of the peregrination. Then you have, this was the road, here is where are the shrines in Arafat. Well, the people spend the day praying, and at the sunset, after the last prayer, they go back to Muzdalifah. That represents that between 2.5 and 3 million people start the trip almost at the same time, with a fleet at that time of around 60,000 vehicles, buses and trucks. You can imagine the collapse. And then we were contracted by a company and the King Saud University to develop a simulation model to try to find alternative solutions to that and things like that. I mentioned before the routes from origins to destination. Well, this was a small but very interesting project in which this is the center of Dublin. This is the Liffey River. And then this is a critical part of the center of Dublin in which they wanted to test different traffic management schemes in order to find the best settings for the routes and the traffic lights. That was our test bed for the routing models. Preston. Preston was a very interesting challenge. They were accusing us that AIMSUN was not able of validating the Preston model. And we found that the problem was that it was a discrepancy between the OD matrix that they were using, that was the typical OD matrix from transport planning fixed for an average day, while the traffic counts they were using, they were for a specific day. So what happens, the traffic count representing around a 10% more trips than that of the average OD. So obviously AIMSUN was very good, but was not good enough to invent or generate from nothing the 10% of cars. But that was the starting point of a model, a project in which I am still working. That is that of the estimation or adjustment of origin to destination matrix based on measurements. And finally, the one that I mentioned before, that is Hessen. This gives you a little overview, and then let me only, well, most of you will be perhaps familiar with that, but maybe others not. Then you can hear a typical use of AIMSUN. You have the actual, incidentally, this corresponds to a project in the city of Vitoria. That was the actual structure. They were the 3 scenarios, and then what we were doing was just loading the model exactly with the same demand, and check which was the performance of each one of the designs. another possibility, okay. Well, this is particularly interesting. This is the project for the tramway in Paris for Avenue Le Maréchal. And that was, the project was including, maybe you can see the situations, you have here the tramway stop, you have the tramway, you will see how the tramway gets to a traffic light and gets priority. You can see that there is green for the tramway, red for the, so that was testing which could be the performance of the system with a priority system for public transport. Well, and this was, I had been, oh my God, I am only at the beginning. Well, let's, I skip this, and then I will try to go very quickly. I have mentioned several times the combinations of artificial intelligence and microscopic simulator. The scheme was very simple. The traffic simulation was used to generate a virtual scenario. Then a traffic models based on the emulation of the traffic measurements from this scenario estimates the state. And then an artificial intelligence that at that time initially was based on a knowledge-based system evaluates and analyzes the state, evaluates the situation, and makes proposal. Then it communicates this to the traffic model, and then the traffic model evaluates this. Well, then there were two complementary approaches. One was an approach in which the initial traffic network was a priori split in areas. What in the terminology we used at that time were the problem areas. And then there was a system of agents devoted to the analysis of each one of them, and it was a supervisor. So it was inspired in a hierarchical control system, with the difference that the controllers in that case were artificial intelligence unit. Another possibility, and that was exploiting the capabilities of this macro-micro approach, consisted in dynamically generating, once a problem was detected, dynamically generating a sub-network of the network around the problem, and then use the AIMSUN in a similar way. That was the architecture. But dealing with large network raises a problem, is that microscopic approaches are that data greedy, and not always we had all the data that we needed. But for some of these applications, we realized that we didn't need the extreme details of the microscopic. What we required was a tool able of acceptably reconstructing the queue buildings and the spillbacks of the queues. And that was the idea of mesoscopic modeling. You can see that here the responsible of that is seated down there, Maripath. And then, very briefly, the basic idea is the following, is that when you assign the traffic onto the network, is a very rough approach, assume that all the travel times are known in advance. And what happens is that the travel times depend on when the vehicle gets to the next link, from one link to the next, and this is dynamically changing. Well, you have here a very nice document that represents this. This was the way in which we come to a dynamic traffic assignment based on simulation, in which the system is just iterating between a route choice and path flow assignment. It determines at each time period, which is the amount of vehicles that are going into each path. And then a dynamic network loading. It could be many approaches. That the one that we use, that she used in her PhD thesis was that on a simplified car following model. And but the car following model was defined, was built in such a way that at least was able of reproducing the triangular fundamental diagram. So that means that the parameters of the fundamental diagram are related to the parameters of the mesoscopic model. With that, we were in conditions of completing this methodology of moving from a very large network, selecting a subnetwork, and this was simulated as a static traffic assignment, this as a mesoscopic assignment, and this getting back to the back to the details with the microscopic assignment. And but this opened the door to many other possibilities, that of enhancing the traffic management systems on opening, in combination with the macro fundamental diagram idea, the possibility of a wide area control, in which you were using this in order to control a gate in, gate out, in order to keep a certain number of vehicles before congestion in the area. But then in that case, you are simulating the large area with a mesoscopic, and then the interior area with a microscopic. But this is in a consistent way, because you are dealing here with individual vehicles and you are dealing here with individual vehicles. But the vehicle here, when crosses the gate, is the same vehicle. You are not changing the vehicle. Okay, then to finish, the road ahead. Well, the road ahead is exactly something like to ask the crystal ball. And I like very much, since I read this book by Roy Scranton, Learning to Die in the Anthropocene. I like very much what he says. Throughout history, civilizations have walked towards disaster because we humans are programmed to believe that tomorrow will be similar to today. Okay, what's possible? Now we have access to an unprecedented amount of new data through the ICT technologies. And this is allowing us to refine this conceptual architecture of traffic control systems. But even more, then in that case, we can improve the role of the artificial intelligence models, because we can use now machine learning process to better identify the short-term patterns in certain parts of the network. But anyway, what I will climb, I'm climbing from, all you know, that is my claim, is not the question of one or other. It's not a disjunctive or. It's an inclusive. It's both. We need both. I will draw your attention to the following. We have here the network, the physical network, the real network with the sensors. And we have here the model that is the virtual representation of the network with the representation of the sensors. And both are dialoguing. Oh my God, this is what now is called the digital twins. Then I came to discover that, like the Molière's bourgeois, I was speaking in prose without knowing I was doing it. Well, this will be a list of the many previous projects in which we had used this type of approach, but we have never called them a digital twin. Something else, because we have access to this unprecedented huge amount of data, what happens when I am tracking a vehicle with GPS equipment? I can get the waypoints, which they are providing me the location in terms of latitude, longitude, and time tags. Then I can process. It's not a simple process. And here is where all the data analytic techniques come to work. And that means that I need to go through a math matching process. From this math matching process, I can get the data that allow me to compute either the link travel times, or for instance, which are the percentage of use between origin and destination at each time period of each of the paths. So I can get a very complete description of the time-dependent mobility patterns. And even more, which is the key component of most of analytical models, is what we call the assignment matrix. The assignment matrix is getting down, if we have various origins, various destinations, but it may be different paths that share a link. Then in that case, was the key component for most of these analytical models is which are the proportion of trips from origin I to destination J, departing I in period R and arriving at link. When do they arrive at the link? At what time period? And this gives me a full dynamic description, and this is the beginning of what we could call a data-driven modeling. Just a question. The next step is a complex optimization model. This was the PhD thesis of Xavier Ros. I think this, I presented this, although we did that, because it's not finished. There is a lot, plenty of alternatives to do that. Even more, no one unique source of data will provide all the information we need. What that means? It means that we need fuse the data. This will be an example of fusing mobile phone data from the socioeconomic data, from census tracts, from the conventional traffic measurements, from the GPS, the data I presented before, tracking the vehicles, and then is put them together. It's like a cocktail, and then you get something that could be useful. Well, I have included here a set of papers that are accessible in which this is described into very detail. But, and I will try to conclude in a couple of minutes, looking into the future, and I enter now in a very personal point of view. And as personal, I am open to discuss. It's not, I don't think I have the truth that has been given to me in a Sinai by a Lord in Britain in some stones. And that. We can look at the future from 2 points of view. One is the new religion, the technolatry. And that means that technology will take us to the paradise. And that means that connected vehicles, electric vehicles, information and communication technology will be our path to the paradise. Then in that case, if we believe that, obviously the new models will be all the models. For instance, rethink the car following model, rethink many things. But my point of view is that this represents assuming that we will do the same things always in the same way, only that using a different mode. So we change the conventional vehicle by the electric vehicle or the connected vehicle. But we still are going from A to B in the same way. There is, and I insist that this is very personal, there is another view. Is thinking that mobility, and because of that, the distinctions between mobility and transportation, depends on many other aspects that are not purely the technology. Depend on social factors, depend on the structure of the city, depend on the distribution of the activities in the city, and things like that. So maybe then the solution is think of doing different things, but they still use the technology to do that. For instance, the 15-minute cities and things like that could be an example of that. Okay, then in that case, we need other type of models. Which models? This will be one of the slides that I will be for 1 hour talking. I will only say a few words, and I hope I will still be able of conveying you the message. Finally, what is essential is the accessibility to the activities. do the activities, realize the activities is what we need, is what makes sense. And if we need to travel, it's because there is an spatial separation in the areas in which the activities. So the activity, the accessibility is at the center, and then we have the other factors, the land use, of which it depends the spatial proximity, the transport system, that in that case provides the physical connectivity, but all these mobility patterns also are influenced by many other factors that are not technological factors. This is why a different way of looking at this is just looking at the activities, and this the sequence of activities that the people do every day. Leave home, takes the children to the school, then from there it goes to the work, then maybe to the supermarket. So is this sequence of activities what makes sense? But to deal with this means, and I insist that this could be even a very provocative, but I think that I am in the conditions of being provocative, proposal, is that we need to change our minds. So far, we are using conventional reductionist approaches. This is the typical mechanistic approach. I split my system in the components and I analyze independently each one of the components. I use the parable of the blinds visiting the elephant. My point is that maybe it's time to change our mind. And that means to think on the complexity of the systems. And cities are complex systems, and complex systems are systems that are composed by a large number of components that interact. And the interactions are as important as the components and the final behavior of the system. And what happens with this type of complex systems? That the behaviors are quite frequently counterintuitive, because I push the button here, but the reaction could be there. I fix the local problem, but I create another problem, unless I take this. So what means? That means thinking of the cities as a large, complex system, and the transport models as one of the complex components of a complex system. Let me put you an example. I have included here the energy as one of the components. It makes sense to think of the electrification of the mobility. Thinking only of the vehicles and the charging points, what about the grid network? Is able to support this? If you go to Barcelona, you will see that we don't have the network to support this. And what about the generation of the energy that we need to supply all not only the energy, even something that is more interesting, the power. Because it's the energy that we must supply in a given period of time. We have a given period of time to supply this energy, not forever. Okay, so because of that, I think that a way of dealing with this is that they are we have the tools. What happens is are not so far not commercial tools. But for instance, we have, well, I will forget a little bit about the urban sim, but I don't know why, but the Berkeley project is not longer supported. It's Weddell retired, and then after his retirement, apparently it came down. But Sim Mobility is the magic project in Singapore. It's with the group of MIT, with Moshe Ben Akiva, is doing. And what they are doing is just building models that integrate all the components and the relationships among these components. So to conclude, I like very much this sentence of Antoine de Saint-Exupéry, Citadelle, pour ce qui est l'avenir, il ne s'agit pas de les prévoir, mais de les rendre possibles. It's what I would like, to make the future possible. And then what is clear for me is that the road ahead, if I have to give some recommendations, will be that thing of which are the cities we need to survive in the Anthropocene. Incidentally, this is borrowed from a group of people that is just thinking of that. There are very nice publications about the cities in the Anthropocene. That means model the cities as complex systems, taking the mobility as one of the components and look at for the integration. Then take into account this activity base as a way of representing the sequential activity. Also, something that I have always found very curious is that we are not taking in our transportation model, we are not including the urban distribution models. While if you do this type of approach, then this could be a type of activities and a chain of sequences of activities, and you can include it in a natural way. And you have this type of approach. Okay, thank you very much for your attention, and I'm sorry if I taken longer than.
Okay, let's try to leave in 10 minutes, 12 minutes, but I think we can take a couple of questions or three. If you guys want, of course. Bye. Any question from the audience? Everything is clear. So some figures.
That school represents that either they agree or they so deeply disagree that they think that it makes no sense to disagree.
No. Well, if there are, yeah, Francesc Magrinyà.
No, well, that's true. And I think that if we look at the set of people that we have in the university, we have the think tank, and we have the possibility. But to be honest, I'm not, despite my attempt to provide an optimistic message, the reality in which we live is not pointing in this direction. A few days ago, I was attending a meeting in a teleconference in a meeting from the ITS Spain on this new invention. Now the revolution is the revolution of the names. You change the name, or you give a new name to an old thing, and then you have found something new. And now we have the data spaces. All people is talking about the data spaces, and again, the data spaces will bring the happiness to all of us. And I was asked a similar question. And my answer was the following. The problem with the data is not the technology. The problem with the data is the problem with the owner of the data. And for those who claim that the data is the new oil of the 21st century, I will recall them what the owners of the oil do with the oil. And this is what the owners of the data do with the data. If you look at the structure that the European community proposes for these data spaces, you immediately realize that in this conceptual structure, there are three types of components. The data sources, the people requiring the data, and then at the top of the conceptual scheme, there are two key names, the broker and the clearinghouse. What means that? That what they are supposing is that there is a business with the data. And that means that someone asks for some data, goes to the broker tells, oh, this is who has the data you need, and then you get to a clearinghouse, and you have to pay for the data. This is partially true if it was only a question of market and financial items. But behind this, there is also a power structure. And that means that the owner of the data is not willing to make the data available for economic compensation. Is the case, for instance, of the administration, because it represents power. And provide the data will represent provide power. And my God, this is the last thing that they will accept. Which is the exception to this rule? Google. Think of the GTFS standards. It's a protocol that has been accepted by all public transport companies in the world. Why? Because if they didn't accept, they will not show up in the estampita, in the picture. No saldrían en la estampita. And then they have accepted. Then either you have the power of imposing something like that or not. What will be necessary, to my point, to have a kind of authority, a think tank with authority, that instead of thinking of the solution of tomorrow, was thinking of the solution for the future. AIMSUN today is impossible to replicate AIMSUN history. Why? Because I am aware that we were living a kind of exceptional period, a period in which just by chance the government gives some money to research. The amount for AIMSUN was substantial at that time. For instance, the computer equipment of AIMSUN was 20 million of pesetas at that time. Translated this in terms of euros, taking into account the inflation and things like that. Incidentally, these 20 million of pesetas, with Mateo Valero, we put together with, they were doubled by the ministry, by Mr. Major, because his daughter was a student of computer science. Then with this 40 million, we put the 40 million together with a grant that the digital equipment had given to Mateo, and with 20 million that Mateo was able of combining Ferrate to be. And this was 100 million that allowed the Faculty of Computer Science to upgrade to a VAX cluster that was the first serious equipment that the faculty. But this is just an exceptional situation. Again, in between 1989 and 1996, the European projects, the ones I have mentioned, Asterix, Clarity, they were not putting us pressure to be successful, productive, and produce something with impact. So we had a period between 85 and 96 in which we were able of working, thinking only on the developments and in scientific terms, obviously with the applied perspective. This is what will be necessary, and this is what I'm not a fan of Singapore, but what Moshe Ben Akiva and MIT have been able of building in Singapore with the SMART, the Singapore MIT Alliance for Technology and Research, for research and technology, SMART. They have a funding of $30 million per year from the government of Singapore. Plus, they have attracted, I'm sorry, I'm not able of translating this into English, is el típico verso aquel de a un panal de rica miel 100,000 moscas acudieron. Well, then you have there, I was visiting Singapore just short before the pandemic, invited by Moshe. And then they had there the sponsorships by Nissan, Mitsubishi, Sony, Toyota, blah, blah, blah. I don't know how many million. And they work like that. Plus, they have been able, because of the authorities, of getting access to all kind of traffic data in Singapore. They have a very nice public transport system, the Metro of Singapore. I was amazed. I don't know if you have had the possibility, you have experience.
Last year.
Yeah. And then they have all the data because you have the contactless and you get, so you are thinking of big data. It's amazing the data they have. They have the data of the taxis. They have the data anonymized. It's not, and then they are building the model. Look at the set of publications and applications that they are developing. This is the think tank. In my next life, when I reincarnate, I would like to be, I told Moshe, I would like to be like you. I don't know if I have answered your question.
Okay, I think they should close this right now. So then let me thank you again. Yeah, it's you made now with the last answer. I was also sad thinking about some examples how we work with 5% of the budget, and we produce not 100%, but 50%, with 5% of the budget that anybody at the international level they get. I'll give you an example. The same company that was funding the chair I was holding was giving some money every year to UPC. They were giving 50 times this amount, 50 every year to MIT. The same company is in international holding. The headquarters are right here at 5 minutes walk. And I say, well, if you give us this kind of money, that was $5 million per year, we can do many things, man. Many things. And one thing is the amount, and then not every year you may give or not. No, please, we need a continuity, no? We need, periods of 3-5 years because we need to hire people, and these projects take a lot of time, PhD thesis, whatever, so you cannot start running and then suddenly next year, well, I'm sorry, no, we don't continue. No, come on, this is not serious. No? So imagine the things that you can do. And then you said some other things. Well, and another warning is besides having very nice tools like AIMSUN, people that know a lot, transportation is a complex. So when sometimes they say, oh, well, it looks easy. Yeah, everything looks easy in transportation, well, except for some formulas that Jaume put. But the concepts are easy. There is nothing that you say, I don't understand. But it's complex. The country, at least in Latin countries, with the best modelers is Chile. They are demand models. They are experts, but they are experts about demand models, internationally experts. And it's a country where they made the biggest mistakes when they tried to change or to design the bus network of Santiago. The same happened at very smaller scale. Probably you haven't heard, but I have, in Santander. A group of people that studied in Chile, the same experts about demand models, but buses are wild, as Hugo knows, and you need to know many other things, not just demand models. Also operations, many things, and it's complex. And so that's why your comment, Francesc, Magrinyà, about a think tank. I have a curiosity. What was the name? Because I'm sure there was somebody with names that was from the city of Barcelona giving money to you to develop models 4 years ago.
Pasqual Maragall.
Okay. Somebody, outstanding. Somebody excellent. Somebody with a very long-run vision. Somebody with very high education. We don't have this kind of leaders today. We don't have this. Politicians are pretty bad, are pretty mediocre. Very short run, no high education, no everything has to be solved in a. They don't care about building something solid, and just little medals, little inauguration, pictures, very trivial stuff. So you were lucky that you had this chance.
Yeah. I am. Is what I say. I am conscient that I was so lucky of living an exceptional situation in Barcelona and in the European Union. That has no repeat. And what I agree with you is that it's not a problem of the people. If you allow me to go back to the literature. Again, I cannot translate this into the English. Es como en el poema de Miocid. Oh, qué buen caballero si hubiese buen señor. Es decir, de buenos caballeros tenemos cantidad. A ver, AIMSUN es un ejemplo de ello. La calidad de AIMSUN es una medida de la calidad del equipo que formaba AIMSUN. Por lo tanto, a nosotros aquello que nos daban cuando acabamos la mili con la tarjeta, la cartilla verde, que era la que nos declaraba libres, que ponía en un apartado, valor se le supone. No. Porque no habíamos ido a la guerra y no lo habíamos podido demostrar, afortunadamente.
Not in my case, but I'll tell you. Not in my case. But
pero, es decir, la cantidad de gente que tenemos aquí sin salir de este campus, cuyo valor no se supone, sino que está demostrado, es enorme. El problema es que hubiese buen señor, lo que tú acabas de decir. Un amigo mío, que fue un político importante también, con Fermí González, clasificava els polítics entre els que saben llegir i escriure i els altres. Bueno, pues el problema és que no en tenim, de que sàpiguen llegir i escriure tenim molt pocs, si és que en tenim algú, però bueno.
Okay, guys, let's thank Professor Barceló. Thank you.